Welcome to ExplainerCast, episode 17. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do today about rainbows.
Yeah, I was thinking this would be a good topic since this time of year we've had a lot of rainbows visible near our house. And so as I've been looking at them and thinking about why do we see them where they are and why do they look the way they do, seemed like a good topic to get into.
And can you go and actually ever walk to it?
Yes, good luck. But we'll talk about why that may or may not succeed.
Yes, fantastic. I've always imagined rainbows are just watercolor in the sky. You know, it's like the colorful stuff that leaks out of clouds. This might not be accurate, though.
Well, it's not totally wrong. They are a phenomenon caused by clouds, and due to some weirdness with the way that light interacts with water drops, the colors do, if not leak out, they spread apart. So we'll talk about exactly what's going on there as we dive into the details.
All right. Well, where do we start?
So I think the first place to start, so there's actually two ways. One way would be to go straight to rainbows. The other would be to talk about what we need to know to understand them. And that would be specifically talking about refraction and color dispersion. So which way do you want to take this?
First principles first.
First principles
How's
first.
that?
Okay. So rainbows, we'll get to them by the end of this, but we're going to start with something simpler. So the physical phenomenon here have to do with light, and specifically the way light interacts with the interface when it changes media. So think about light going from the vacuum of space into the air of our atmosphere. That actually changes it a little bit, but not much. But then when the light that's traveling through our atmosphere enters or exits a body of water or like a piece of smooth glass, like some light transmitting material, then the light is actually disturbed by that transition in a pretty substantial way. And so we see a couple of things. The first one is if you have a mirror, then you're used to seeing light reflected by that surface. And this essentially is the electromagnetic waves of the light interacting with the properties of the mirror surface to essentially retransmit or reflect that light ray back off the surface, essentially bouncing off of it like you would expect like a ball to bounce off that surface as well. And we say that the angle of reflection, the angle it bounces back from the surface is equal to the angle of incidence, meaning the angle that it came at the surface. So if it comes in sort of perpendicular, like straight towards like the screen I'm looking at, it'll come straight back at me. And if it comes in at an angle, it'll kind of glance off and come off at an angle. So that's the first thing. The second is if we have a material where instead of just bouncing off and reflecting, the light actually enters into that material, say, again, into like a lens, like a piece of glass, or maybe into a body of water, then the behavior is a little more complex. And we call this something called refraction. So as the light enters the new material, it will change speed and it will change direction. And so this is a little bit kind of strange, actually. So we talk about the speed of light. And Dave, do you have the speed of light memorized?
3 times 10 to the 8th meters per second?
Yes.
Is that right?
Yeah, that is. So that's like...
Oh my gosh.
That's like,
I have not thought about that number in a while. That just came right out.
That's pretty good. So that's 300,000 kilometers per second. And when I was a kid, I learned it as 186,000 miles per second. They're about equivalent. So specifically, though, that's the speed of light in a vacuum, meaning essentially empty space. And
with nothing impeding its flow.
That's right. Yeah, nothing impeding its flow, nothing to interact with in the electromagnetic, I guess, regions or realms. And so as light enters other materials, even our Earth's atmosphere, it slows down a little bit. And so in the atmosphere, it slows down very little because our atmosphere is a gas and the particles are pretty far apart. But as it enters other media like water or glass, it actually slows down quite a bit. And the change in speed is measured as something called the index of refraction. And this can be a number like, I'm trying to remember what it is now for water. Is it like 1.3 or something like that?
And what does that mean exactly?
Yeah, so the index of refraction has a couple of different meanings, and they describe how light interacts in that material. The one definition is it represents the ratio of the velocity of that light wave or that light, I guess that photon or light particle in the medium compared to the velocity in a vacuum. So velocity in a vacuum is going to have an index of refraction defined to be 1.0. And in most media, the light will slow down in that medium, and the amount it slows down by is going to be the index of refraction. So for example, in water, I think it's around 1.3. And what that means is that the speed of light in a vacuum is, again, 3 times 10 to the 8th meters per second. The speed of light in water would be that number divided by 1.3, so about 30% less.
Yeah, makes sense.
So that would be like 2.3 times 10 to the 8th meters per second. So instead of going 300,000 kilometers per second, it might go only 230,000 kilometers per second when it's in water.
Just really slow. I mean, just slowing on down. It's like a mosey.
Yeah, so much slower. And there is a case where this is important. And there's many cases where it's important, but one that I think about some is to tie this into some of the other topics we've discussed with data networks. Light moves more slowly in a fiber optic conductor, a light conductor, than it does in the atmosphere. So there are two things that add latency to fiber optic systems in the transmission of light itself. One of them is the fibers usually don't take a straight path. They're usually following city streets or rights of way, so they're not going point to point directly. But the second is that the light that's flowing through them is actually going quite a bit slower. And for some other beneficial properties of those fibers, they might even go slower than they would in the example of water. Like the index of refraction is often even higher for those types of glass. And so the light might be slowed down to maybe half or 2/3 of its speed in a vacuum.
Wow.
And so that's significant.
Oh, that's a lot.
Yeah, when you're traveling an ocean distance, that's significant. So why does that matter? Why does it matter that the light slows down when it enters kind of these denser media and then it speeds back up when it exits them? The reason it matters is when the light crosses from one medium to another, and they have different indices of refraction, so say from air into water, then associated with this change in speed will actually be a change in direction of the light as well.
Yes.
And so this is why lenses can bend light and they can focus it, or they can change the shape of things we see through lenses. And it's because as the light enters the thicker medium or the denser medium, the medium with the higher index of refraction, it will bend in a specific way. And to understand that, we have to understand one more geometric concept, and that is at any point or local neighborhood of this interface between two materials, we can think of what is the orientation of the plane that defines that interface. So the two-dimensional plane, and we can think of it as being a little flat plane. And like imagine if you were on the Earth and you wanted to think about, well, what does sort of level mean? And then specifically what's perpendicular to that? We call that the normal direction. So imagine like you're planting a flag on the Earth and you want it to stick up straight up and down. It's going to be perpendicular, which means it's a 90-degree angle to the local direction of the Earth right there. And when we're thinking about refraction, we again think about this normal vector or this normal direction. And so in the local area where, say, a ray of light is entering a medium, as it enters a medium with a higher index of refraction, it will bend toward that normal vector based on the ratio of the indexes of refraction of the medium it's exiting and the medium it's entering.
Okay. So are you saying that for a medium with a higher, greater than 1 refractive index, that the incoming vector will bend to be less closer to in angle the normal vector?
Yes.
Once it enters.
Yeah.
Is that what you're saying?
Yeah.
So if it comes in at like 45 degrees, and it's going into a water,
Yep.
it might go to 40 degrees or something. It's like
From the normal.
No, I might got that. Yeah,
Yep.
45 off of the normal. Yeah.
Yep.
Now it'll be like 40 degrees or something. I don't know the actual number, but
Yep.
just in that direction. It won't go to 50 degrees. It'll go the opposite.
Exactly. It'll bend toward the normal vector, sort of away
Okay.
from the surface, if you will.
Yeah, that makes sense.
And then this relationship is perfectly inverted on the way back out. So a light ray that's coming out of the higher refractive medium, the higher index of refraction, will bend away from the normal and sort of toward the surface. And so
Okay, so it becomes parallel with the original vector.
yes. And so if you were to enter the medium and bend and then be perfectly reflected back, it would follow, the reverse path back out.
Okay. Oh, cool. Yeah. That makes sense.
Then one other thing, so this, like if you're looking into like a lake or a pond that has a very smooth, clear surface, and you put like a stick into it that is going through the surface, you can see this where the stick appears to bend as it crosses through the surface. And the stick's not actually what's bending. What's bending is the light that's being reflected by the stick or scattered by the stick back towards your eye. When that light hits the surface, it bends away from the normal vector. And so you see this kind of change in angle that makes it seem like the stick is actually somewhere else because your brain assumes that the stick is directly in the direction that your eye is seeing.
Yes, and it really is trippy. It's like, oh my goodness, that stick is like, it's a hard angle too. It's just like an instant bend at the surface of the water. And then beyond that, the stick looks normal, just poking out in a really weird direction.
Yeah. And so because the amount the light bends is a function of the angle that the light is crossing the interface at, if you put a stick in the water and you sort of look at it, say straight down from above, it's going to look pretty reasonable. But as you like bend down and crouch to the side,
you might, Shane, you might even say it looks normal.
You could say that. Very nice. And then as you kind of crouch down from the side, though, the degree of deviation you see will increase because that light is coming out at a further angle from that normal vector, and it's going to bend yet farther away from that vector accordingly.
Got it. Okay.
And one more thing, if you were to crouch down low enough to where you're looking almost across the surface of the water, there'll come a point where the portion of the stick under the water disappears because instead of seeing into the water, all you're seeing is a reflection off the surface.
Yes, after a certain angle, the light will no longer refract into the water, but instead reflect off of it.
Yeah, and in the other direction, the light that's trying to come from the stick under the water back up to the surface in particular, when you're going from a high IOR to a lower index of refraction, again, recall it's trying to bend away from the normal. It's trying to bend toward the surface. There actually comes a point where it's already at such an angle that's close to the surface angle and very far from the normal angle that geometrically it can't satisfy the physics equations by staying above, like by actually crossing through the surface. And it'll actually, it totally reflects back into the higher index of refraction medium. That's called total internal reflection. And that happens on a water surface. And you can see it from inside a swimming pool as well. If you go below the surface and you look straight up, you can see. And as you look out towards the horizon, you'll get to where all you're seeing is the underside of the water surface. And this is also a key property that makes fiber optic transmission lines work. The laser that is shown into the fiber doesn't perfectly usually travel straight down the center of the fiber. It kind of bounces off the sides of the fiber, and they rely on the total internal reflection to keep the majority of that energy from that light shining into the fiber to stay within the fiber, even as it curves and bends through the city streets and the other infrastructure to get to its destination.
Very cool.
So now there's one more physics phenomenon we need before I think we're ready to talk about the natural phenomenon of rainbows. And the last phenomenon is that we talk about the index of refraction of a medium, like water being maybe a little higher than 1.3. But when we say that, we're actually only speaking about one particular color or frequency or wavelength of light. It turns out that different electromagnetic waves at different frequencies will actually experience a different index of refraction in most media. And for visible light in, call it sort of typical media, the higher the frequency, the greater the index of refraction, meaning the more it slows it down, and thus meaning the more that it is going to change direction and bend as it goes into or out of that medium. And
Okay, so remind me on the visible spectrum from red on one end to violet on the other, which one is the higher frequency?
the violet side. Yeah, so red
Okay.
are longer waves, lower frequency, and then as you move through the spectrum up to the blue and violet side, those are the shorter wavelength, higher frequency. And so those are the colors that bend more, and the reds are the colors that bend less.
Okay.
And so this ends up being important when you look at rainbows, and this property that different colors or different frequencies bend to different degrees leads to a property called dispersion. And the idea here is that what we perceive as white light is typically a mix of many different frequencies of light. And when a ray of white light crosses one of these boundaries and refracts, the different wavelengths or frequencies or colors, all compatible definitions, will refract by different amounts slightly. And this is what gives rise to our ability to see the spectrum, the various colors associated with white light, whether we're using a prism, which is like an angular object, usually made of glass, or as we'll get to in a rainbow. And so white light comes in, it bends, the red light bends a certain amount, up through the blue bends a little bit more, and so then those colors are spread out.
Awesome.
And we were talking before we started about, turns out both of us have some prisms hanging in our house, and so when the sunlight hits that prism and it goes from air into glass and it refracts, and then maybe it has some internal reflections, and then it comes out one of the faces of the prism and it's been refracted, that incoming sunlight has been dispersed into the different colors, each occupying slightly different angles. And then when that dispersed light hits something like the wall, then we actually see a rainbow projected on the wall.
Awesome. So we have diffraction, dispersion, and different amounts of, or I guess it's dispersion caused by the different frequencies. I was going to say, is that a third phenomenon, or is that the same? That is dispersion, the concept that different frequencies refract at different angles.
Yeah, diffraction is something else, but yeah, that they refract at different angles is what leads to dispersion.
Okay, got it.
Which is the spreading out of different frequencies or colors. Okay, so now we've laid, I think, the necessary groundwork to talk specifically about the rainbows we see in nature. And these are different than the rainbows we see in our prism example, where we're shining a light into an object and causing the colors to disperse, in a projected manner. And so in a rainbow, essentially what's happening is that light from the sun is entering a water drop. And the typical way that we think about how to define, how to derive, I should say, a rainbow, is think about water drops as spheres. So little ball-shaped blobs of water. And there's usually rain or a mist, and the sun has to shine on it. And as the sun shines on these water drops, some of that sunlight in fact, most of the sunlight will pass through the water drops and be refracted and dispersed on the way. But some of that light will actually enter the water drop and be reflected by the far surface of that water drop, the side away from the sun, and it will then bounce back toward the sun. And so
okay,
if we, the viewer, are standing with our back to the sun and we're looking at airborne water drops, like usually rain or a mist that's being illuminated by the sun, we can see some of this light being reflected back to us. And it'll often look a little bit brighter than maybe some of the surrounding area. And the crazy thing is that not all of the light being reflected back is coming back uniformly, because these aren't a bunch of just flat mirrors. Due to the spherical nature of the water drop, the water that enters the center of the drop is going to bounce straight back.
The water that enters the center of the drop is just going to bounce straight back to the sun.
That's
and
right.
You have no visibility of that, right?
I mean, if you have the sun directly behind you and you're looking straight away from it, yeah, I mean, you'd see it. It's just going to be a little bit of white light coming back to you. And again, most of the sunlight goes through it, but a certain percentage bounces back.
Yeah. Okay, got it.
But it gets more interesting as you start to think about the rays of sunlight that are hitting the water drop, not strictly on center, but a little bit at an angle or a little bit off of center. And so as those enter the water drop, they're hitting the sun-facing surface at an angle relative to that normal vector. And that means that they're going to bend and refract into the water drop a little bit toward the center of the drop, but not enough to pass through the center. They'll then hit the back of the water drop. And again, some will transmit out, but some will be reflected back toward the front of the drop. But again, they're not going to come out the center of the drop toward the sun. They're going to come out at an angle relative to the sun. And they'll be refracted once more and actually bent a little bit back towards the sun. So when they enter, they bend toward the center of the drop, they reflect off the back of the drop, and as they exit, they kind of bend back toward the sun. And so as you look at the angles of different sun rays hitting a water drop, and you move closer and closer to the edge of the drop, this pattern happens where the angle they bounce back at changes less and less until it actually stays about the same for a certain range of inputs. And then they start to diverge again. And so what this leads to like a focusing effect, where there's a certain angle where the reflected light is brighter because you're actually gathering and concentrating a certain amount of light that came in at multiple angles and all came back out at the same angle.
Okay.
And for visible light, this specifically happens at a very specific angle due to, again, the refraction and refraction and reflection within a water drop. And it ends up being an angle of 42 degrees offset from the incident angle that the light was coming in.
It had to be 42, didn't it?
Had to be 42, right? Life, the universe, and everything. So I hadn't even thought about that, but that is awesome.
Oh my gosh.
So now we can start to actually figure out where we're going to see what becomes a rainbow. So we've got, let's say, the sun at our back, and we're looking at a rainstorm, and what you're going to see is if you took the angle from the sun, like through your head towards this rain, and you were to then measure a 42-degree angle away from that, that's the edge of this reflected light coming back to you. And it's brighter there. But furthermore, because each color of visible light refracted slightly differently in that raindrop, that is where you actually see the dispersion of that white light into the visible light spectrum.
Okay, 42 degrees. I want to make sure I understand this. Do I have to be standing where I will intersect a vector that's coming 42 degrees off of the sun's rays?
Yes.
Entering a water droplet? Okay.
Yes.
So anytime I see a rainbow directly in front of me, say I'm like in the center of the arc, and I'm staring right at it.
Yep.
42 degrees off of that to either my left or my right, I will find the sun?
No. So the sun is, if you are staring straight at a rainbow and the left and the right sides are sort of equally to your left and to your right, like you're staring in the middle of it, the sun's directly behind you.
Oh, okay.
And if the sun were at the horizon, if this happened at sunset, the top of the rainbow would be 42 degrees above the horizon. The left edge of the rainbow would be 42 degrees to left of your center of field of view.
Yes.
And the right would be 42 to the right. So it traces a perfectly circular arc.
Okay.
Now, as the sun is usually not right at sunset when we see these, but it's some distance above the horizon, essentially, if you picture in reverse, the sun rising above the horizon, I mean, I see these a lot at sunset, but imagine it's at sunrise. As the sun is rising above the horizon, that circle stays centered on the line from the sun through your eye. And so essentially the rainbow would sink down into the ground as the sun rose.
Okay, got it.
And so we don't usually see a full circle because the Earth is in the way, but this phenomenon would actually trace a full circle of arc radius 42 degrees, essentially. We just only see the part that's typically above ground.
Yeah. And there's no water droplets below the ground. There's something in the way of the light.
Yes.
It's the Earth.
That's right. That's right. Yeah. Yeah. If you had so if your vantage point were far enough above the Earth and you had a cloud, you could, in theory, see like a full circle rainbow.
Yeah. So like how high, I mean, I'm not going to make you do math in public, but how high would you have to ride in your helicopter to have a full circle at the ideal positioning of the sun?
So this is what leads to another piece of this is the angle is what's important, not the distance. And so the question is really how far away are the water drops that are creating the rainbow? If they're close by, you don't have to be very high to see this. But if they're far away, then you would have to be higher because the circle is essentially going to get bigger in proportion to the distance. But it'll always look the same. It'll always be the same angle. It'll just be a question of how far away it is.
Okay.
So the 42 degree number, it's close, but it's approximate. And that is for the red frequency that we perceive in visible light. And so the other colors of the visible light spectrum, orange, yellow, green, blue, violet, all are higher frequency. They bend and refract a little bit more as they enter that water drop and exit that water drop. And so they actually appear on the inside of this 42 degree circle. And so if you go look at a rainbow, you will see that the outer edge of it is the red edge and the inner edge is the violet edge.
Okay, cool. Yeah.
And you'll see inside of that, you'll actually see that it's brighter inside that circle than it is outside that circle. Because all of this light that's going into the water drop and reflecting once and bouncing back toward us is inside that 42 degree circle. None of that light is outside of the 42 degree circle.
Because the higher the frequency, the more it refracts, or the bigger the angle it refracts. So
yeah, it comes more towards
the 42
center.
degrees is the maximum refraction angle. Okay.
Yeah. Yeah. And again, it's due to the spherical geometry that it does that. And so there's actually like a brighter area inside and a slightly darker area outside. And so one way I've started thinking about a rainbow now is what you're really seeing is you're seeing a series of overlaid color discs. And it's only at the edges where the different colors are kind of separated and you can see like which color extends to what distance along the edge of the rainbow. Kind of a weird way to think about it. So a couple other interesting things then. If the rainbow I see is a function of the sun and myself and then this 42 degree angle, that means if you're standing somewhere else, maybe you're standing next to me, maybe you're standing a mile away, unless you're directly in front of, well, actually, no matter where you are, unless you're looking through my eyes, you are seeing your own 42 degree circle defined by the sun and you and your eyes. And so you're actually seeing a different rainbow than I'm seeing. And same with everybody else.
Yeah. It's your own private rainbow.
We each see our own. Yeah. And
every rainbow is custom.
Exactly. Exactly. And now we might be sharing some of we might be looking at the same rainstorm. We're seeing the same water drops, but I'm seeing maybe the red that's coming from one of these water drops, and maybe you're a little bit to the side, and so you're seeing the blue that's coming from that same water drop. Or you're just seeing an entirely different set of water drops altogether based on where you're standing.
Yes. That's so cool to think about.
Yeah. And this also is what makes it difficult to actually go to the end of the rainbow, because the reality is as you walk toward it,
it moves.
It's going to move because its definition.
It's actually not moving. You're seeing a new rainbow every time you step away.
That's right. There actually isn't just one. There's this whole collection of them, all custom for each viewer. And because they're defined specifically to be off to the side from your viewing position relative to the sun, you sort of can't like as you walk toward it, it will change because your
Yeah.
angle to the sun changes as you do that as well.
It's so elusive. I mean, I've tried to find the pot of gold so many times, but it just, no matter how fast I run, no matter how far I go, it's always 42 degrees away.
Yeah. Well, this discussion may put a hamper on your business plan then, but we'll see.
I know. I need to send a helper, and I'll tell them where to go.
That's right. You need to direct them. So then one more thing to think about, and again, we've seen a lot of these here. And so a couple things that this brings out. This means that if you're earthbound and you want to see a rainbow and you're on a relatively flat place, then you're only going to see it when the sun is within 42 degrees of the horizon. So midday when the sun is high in the sky, you're not going to see these. And again, where we are, I tend to think of, we talk about rainbow weather, like when it's like sunny and there's localized rainstorms, because if there's rain everywhere, then the sun's not shining. And it has to kind of be sunny in spots, of course, but also it tends to be morning or evening when the sun is low enough in the sky that it can actually shine below the cloud and hit the rain and then be reflected back.
Right. So does that mean that anytime there's water droplets in the sky, there's always a rainbow as long as you can put yourself in the right vantage point to see it?
I think as long as there's direct sunlight hitting those water drops, the answer would be yes.
I guess that brings you hope. Don't worry, there's a rainbow somewhere.
Yeah, as long as the sun's hitting it, if you can see the sunlight illuminating water drops, then you just need to go put yourself between the sun and that water and get your 42-degree angle, and that's where it'll be. And so this actually gives you a way to, like if you have a sunlit waterfall, for an example,
Oh, yeah.
then you put yourself in the right place where that 42-degree angle kicks in and you should be able to see a rainbow.
Yeah, in fact, I think it's very common to see rainbows at waterfalls in the right time of day.
Yep.
You know?
Yeah, exactly. Based on the angle.
All because of the mist they kick off.
Yep. Yeah, fine water drops. And this doesn't seem to be particularly dependent on the size of the water drops. It's really dependent on their shape, as long as they're spherical or close enough to it. And so, again, fine mist or a rainstorm with larger drops, it seems to work.
Oh, it works with larger droplets? I mean, I would imagine raindrops that are big get deformed out of a spherical shape as they fall.
Yeah, that's true. Then they would, I agree with you. So big enough drops that are falling are going to behave differently, you're right, than like a mist that is more kind of suspended in that spherical shape, where the surface tension holds it as a sphere. I think that would be true.
Yeah, exactly. So there's not enough mass that it gets tugged in one direction and skewed.
Yeah. Yep. So one more thing to add into this is the concept of a double rainbow.
I was going to ask, and I'm so glad you mentioned it.
Okay. So give me let's describe briefly, if you would, like what is a double rainbow from your perspective?
Well, now, using some of the terminology we've just described, now I would actually consider it to be a concentric rainbow, meaning you've got one rainbow that you can see, and then if you kind of project that circle out with a bigger radius, there's another one there, or can be.
Yeah.
Another one there. I don't even know the right ratios, and I'm just trying to remember the distances. They're never right next to each other. I know that. There's always a healthy amount of space between them.
Yeah, there's a gap.
And I'm just starting to wonder, like, are you going to say the number 84 degrees here? Is it like some kind of repeating pattern?
No, it's more complicated than that. But you're right. There is a gap, and so the way that we get the single rainbow is there's a single reflection of the light inside the water drop. And the second rainbow, the outer in the double rainbow, and it is on the outside, is due to a path where the light ray reflects twice in the water drop. And the way that the rainbow itself forms is similar, where there are many pathways that the light can take through a water drop that'll reflect twice. But as the light is entering the water drop kind of near the outside edge, it takes a specific path where it refracts into the water drop a little bit, and it sort of bounces off, like sort of not in the center of the water drop on the back center like a single reflection does, but it's low enough or high enough, it's far enough away from the center that it sort of bounces in the back and crosses the water drop and then it bounces a second time and it comes out the front. So it kind of makes
Okay.
like not a triangle shape, not sort of a rectangle, but something kind of in between. And
Okay.
and when it does this, again, due to the shape of the circle and the paths that it can take, and the fact that if it's too close to the edge on the way out, it'll be totally internally reflected, there is another angle, and it's about 51 degrees when you're looking away from the sun, where the brightest part of this two reflection pathway occurs.
Oh my gosh. And is that why they tend to be a little bit dimmer?
Yeah. Yeah, it's just less light because on each of these interface points, it can either cross out and refract or it can reflect. And so a fraction of the light is lost to transmission, and then a fraction of the light is reflected. And so, yeah, it's just there's less of it that's taking this
Wow.
2-bounce path.
Amazing. And so theoretically, is there a 3-bounce path?
I think there are. I think they're very hard. I think, in fact, there are many, many more pathways, up to relatively large numbers, but they're all much fainter. And so we with human eye don't typically see those. I think scientists have measured some of those using more specialized equipment.
So you're saying the elusive triple rainbow is not a myth?
I would expect that it exists. I haven't looked at it myself to see like where it would be. You'd probably need like a very dark background and a very brightly lit set of water drops to get that to work, I would think.
Okay.
The other weird
life goals, I think.
There you go. Someday to see a triple rainbow. The other interesting thing with the double rainbow, so the single rainbow is sort of this disc that is centered at the position when we look straight away from the sun, and it forms a circle of radius 42 degrees, and it has red on the outside, it has blue on the inside, and then it's bright in the interior of that disc. The two reflection path, the second order rainbow, the most common double reflective path actually is, think about entering the center of a water drop, being reflected by the back straight toward the sun, and then being reflected by the front of the drop straight back to the back again, and then exiting the water drop. So it actually transmits the light in the same direction as the sun. And then as you move off center, you start to change the angle until eventually this two-hop path actually is bouncing back toward the sun. And so the bright portion of the second order reflective pathway starts at facing the sun and wraps all the way around the sphere of our vision until the edge gets to that 51 degree mark. And so it's sort of like it's inside out. Instead of looking at a disk away from the sun, it's actually this most of a sphere starting at the sun side and wrapping around our vision. And so there's two weird things.
I'm having a hard time visualizing that one.
I know. I wish I had a better way to explain it. But essentially think of it as inside out compared to the first one. So what this means is actually on a double rainbow, the red edge is toward the center of our field of view. So the red edge of the inner rainbow is facing outward, and the red edge of the second rainbow is facing inward. They're actually facing each other.
Yeah, they're backwards.
Yeah, it's backwards. And then the blue is on the outer edge of the second rainbow. And then all the white, that's just all the mixed light that we see from these other reflective paths, is further outside of it, all the way back around to the sun.
Okay.
And because the sun's shining,
I don't think I had ever noticed that.
I had not noticed it till I started trying to understand the double rainbow thing. So I'd learned about the single rainbow phenomenon a long time ago, and then I was trying to understand double, and I learned that it's the inverse. And so I went and looked at some pictures I've taken of double rainbows, and sure enough, the color order is that way.
They are.
And
as soon as you said it reflects multiple times or twice internally before exiting, I was like, oh, that's like looking in a mirror 2 times. It's going to be reversed back again. So
right.
I was like, I know it's going to be backwards.
Yeah.
And I was pulling up images frantically while you were speaking online, and sure enough, yep, there it is.
Yeah. So that's so cool. When you see this in real life now, you'll have to look at the direction of the colors, and so you could even say, if for some reason the inner rainbow were obscured and you only saw the outer, would you be able to tell? And the answer is yes, because the red.
Yeah, you'll know if you're looking at a double rainbow or not.
Yeah, exactly. The red to blue will be in the opposite sides. And the crazy thing is that means that this region between the two rainbows is a region that those water drops you're looking at are not able to transmit light with a 1 or 2 reflection path. And so they're a little bit darker. The region between the two rainbows is darker than the region inside the inner rainbow or the region outside the outer rainbow.
Yes, I can see that in the pictures as well. So it's actually darker between the bows.
Yeah.
And that's not because of any inherent property of those water drops. It's just because of the amount of light that's reaching back to your eye.
Exactly. It's like this little dead space that they can't send light back on those particular angles very efficiently.
Back to you. Like they're sending it back to all around you and other places just the same as they were any other time.
That's right. Yeah.
But you are perceiving less light in that moment just because of angles.
Exactly.
That is so cool.
Yeah, I think
that is so cool.
As I've been thinking about this phenomenon, that's like one of the weirdest, craziest properties of it is that there is this dark zone. So I got to go look for that next time we get some good rainbows here.
For sure. I mean, that is so interesting. It's like an eclipse inside the rainbow band, inside the double rainbow. It's so weird.
Man, the 90s are calling and they want their lyrics back, Dave.
A total eclipse of the double rainbow. Yeah, it is very strange because it's not actually darker in there. In fact, those drops, there's nothing physically different about them.
Yep.
It just happens to be where you are standing. The light that's arriving at your eye is a different quantity.
Exactly.
And if you were to take 20 steps forward, you would perceive the same phenomenon, but it would be in a slightly different position in the sky as you perceive it.
Yeah, exactly. And yeah, you could move to a position where for what appears to be that dark region, you could change your position to where that's the bright part of the inner rainbow. For somebody else, it is. Or some other position, it exactly is.
Because every rainbow is custom just for you.
That's right.
That is so cool.
Yeah, one other.
So
go ahead.
I gotta ask. So in the case of the theoretical elusive triple rainbow, would it be reversed again? The order of the colors?
I think if I had to flip a coin, I'd say yeah, because I think every reflection reverses the red to blue gradient, and so assuming there isn't some other weird geometric thing that takes place when you're reflected 3 times in the water drop. I don't even know what that path would look like. But yeah, I would expect it's going to reverse the gradient back to. And
maybe it's not possible to have a 3 path. Maybe it has to be 4. I don't know. In which case it would go back to the reverse. Who knows? I'd love to look more into that.
Yeah.
I also want to point out that as I'm looking for rainbow images online, you can spot the fake double rainbows because the colors are in the wrong order. I've actually seen like 7 of them now.
Nice.
Where somebody just photoshopped the second rainbow and they forgot to reverse the order. And that's a lesson for those that don't listen to the show, is you're just destined to make silly mistakes like that and be spotted as a fraud.
Yeah. So yeah, if the first wave of Photoshop debunkery was the shadows are wrong, and the second wave was the reflections are wrong, the third wave is going to be the rainbows are wrong.
The order of the colors is wrong. We can bust this so many ways.
That's right. All right. Well, this was a daunting task, but did we succeed? Do you think we've explained rainbows?
I think we had some explaining to do, and I think we did the explaining, and I think we did just as best as we possibly could without visuals.
Yeah. That's the real handicap here. All right. Well, this was fun, Dave. I hope it worked, and we'll see you next time.
Thank you.